So today we've been asked to find the remaining zeros given 1, 0 for the function. Now, the function we've been given is f of x equals x to the fourth plus 19x cubed plus 131x squared plus 409x plus 520. X equals negative 3 plus 2i. Now, whenever a polynomial has a complex, which is in this case, or an irrational zero, they're always going to come in pairs. And if you think about the quadratic formula, right? If you think about the quadratic formula, minus b plus or minus square root of b squared minus 4ac all over 2a. If you think about this, anytime you have this radical, it's always going to be plus or minus. And so an irrational number, which is caused by a radical, or an imaginary number, which is caused by taking the square root of a negative number, is always going to come in a pair. And that's true for any polynomial. So, if I have negative 3 plus 2i, I know that x also equals negative 3 minus 2i. Okay? So, basically, I know that there are 4 zeros, up to 4 zeros for this polynomial, because it's fourth degree. They gave me 1, but because it's a complex number, I immediately found a second one. Okay, immediately found a second one. So there's 2 of the zeros for this function. They want me to find all 4 of them. Well, there's 2 of them. Well, how do I find the other 4? Well, the easiest way to do that, the simplest way to do that, is to take what I already know and synthetically divide this polynomial to see what I have left. So, I'm going to take this polynomial and write down the coefficients 1, 19, 131, 409, and 520. And I'm going to synthetically divide this by, I'm going to start with this root that I came up with, negative 3 minus 2i. So negative 3 minus 2i. Copy the 1 and then multiply. What is 1 times negative 3 minus 2i? Well, it's negative 3 minus 2i. Combine like terms, which is right there. 19 minus 3, you get 16 minus 2i. Okay? Then you're going to multiply negative 3 minus 2i times 16 minus 2i. If you're unsure, go out to the side and do this work. Type, go in and just write in negative 3 minus 2i times parentheses 16 minus 2i. And you can use the FOIL method, and when you combine like terms, what you should come up with is negative 52 minus 26i. Okay? And you've got to remember that you're going to get negative 2i times negative 2i, which is positive 4i squared. But I squared is negative 1. So make sure you combine your like terms appropriately. Well, what's 131 minus 52? And again, I'm not doing anything with the I because there's no like terms. Remember, I'm adding here. There is no like terms, so I'm adding. So what do? Well, combine our like terms, negative 52 plus 131, and I get 79 minus 26i. It's pretty much all we can do. So then, negative 3 minus 2i times 79 minus 26i. Combine your like terms, you should get negative 289 minus 80i. Okay? And when you combine like terms, 409 minus 289, you should get 120 minus 80i. And if you say negative 3 minus 2i times 120 minus 80i, you should get negative 520, which gives us a remainder of 0. Now that's important because if this is a 0 of this function, it should give us a remainder of 0, and it does. So we know that the 0 I chose as a pair to the one that was given is correct. Now, here's the thing you got to remember, folks. What you actually have at this moment is a new polynomial. And that new polynomial is going to look something like this. It's going to be And I'm just going to scratch this over to the side in red using these coefficients. Now, the original was x to the fourth, so this is going to be 1x to the third, so x cubed, plus 16 minus 2i x squared, okay, plus 79 minus 26i x, then plus 120 minus 80i as a constant. That, marked through my x squared, is what these coefficients tell me. Okay? That's a pretty messy polynomial. But now I want to synthetically divide that polynomial by this 0. Okay, so I'm going to show that work. Okay, so how do we do that? Well, the same way we did the first time, only this time it's a little messier. Well, it looks a little messier anyway. We have 1, we have 16 minus 2i, we have 79 minus 26i, we have 120 minus 80i. And we are going to synthetically divide by negative 3 plus 2i. Okay? Just like always, copy the first term and multiply. We get negative 3 plus 2i. And what happens when we add? These will cancel. So we get 16 minus 3, which is 13. Then multiply negative 3 plus 2i times 13. Well, that gives me negative 39 plus 26i. And what happens to the i's this time? They cancel. And 39 taken from 79 gives me 40. Well, negative 3 plus 2i times 40 gives me negative 120 plus 80i. And that goes away, and that goes away, and I get 0. Okay, what does that tell me? If I get 0 as a remainder, this absolutely did have to be a root to the original equation. So there's 2 of my answers. Now you have to ask yourself, what am I left with? Well, I started with a 4th degree polynomial. This answer here that I wrote in red is a 3rd degree polynomial. So now this is going to be a 2nd degree polynomial. Okay? And a 2nd degree polynomial is a quadratic. And a quadratic can very simply, very easily either A, be factored, or B, use the quadratic formula. Now in my case, I look at the factors of 40, and I see the factors of 40 are 5 and 8. And 5 plus 8 makes 13. Okay? And so I think this very easily, very simply says to me, oh, I can do that. So this factors into x plus 5 times x plus 8 equals 0. And of course, this will give me a root of x equals negative 5. And this will give me a root of x equals negative 8. And so we have negative 5, negative 8. So what are our 4 roots? Well, they gave us 2 of them. So down here at the bottom, we could write all 4 roots. Negative 3 plus 2i, negative 3 minus 2i, negative 5, and negative 8. And there are the 4 roots of this polynomial given in the original problem. There are your 4 solutions. So it has 2 real solutions and 2 complex solutions, and there's all 4 of them. So similarly for problem number 2 here, we've been given a polynomial, 2x cubed minus 5x squared minus 2x plus 15. And we've been given a root, and we're told that x equals negative 3 over 2. So I can synthetically divide this, negative 3 over 2, and my coefficients are 2, negative 5, negative 2, and 15. And if I copy the first one and then multiply, well, negative 3 halves times 2 is negative 3. and negative 3 and negative 5 add up to give me negative 8. And if I multiply negative 8 by 3 halves, I get 12. And 12 minus 2 is 10. And if I multiply 3 halves by 10, I get negative 15. And 15 and 15 there give me 0. And that 0 tells me that this is, in fact, a root. This is, in fact, a 0. Okay? More importantly, though, what I get is what I'm left with. What does this mean? This means I'm left with 2x squared minus 8x plus 10 equals 0. This is what I'm left with. And I say, okay, does this factor? Does this factor? Okay? So I look at it and I say, no, I don't think it factors. Okay? But we can try. Let's try. So if I factor out a 2, I'm left with x squared minus 4x plus 5 equals 0. And the factors of 5 are negative 5 and negative 1, which add up to negative 6. Or positive 5 and positive 1, which add up to positive 6. Not going to get negative 4 out of this. So, if it can't factor, what do I have to do? I have to use the quadratic formula. So I say, okay, the opposite of b plus or minus b squared minus 4 times a times c. Well, 4 times 1 times 5 is negative 20. Okay? All over 2a, which is 2. So what do I get? Okay? I end up with 4 plus or minus the square root of negative 4 over 2, which is, if you follow me on my paper here, is going to be 4 plus or minus 2i over 2, which is, if you divide everything in here by 2, you get 2 plus or minus I. Okay, 2 plus or minus I. This is a pair of zeros. You have 2 plus I and 2 minus I. That's 2 zeros. They gave you 1 0, so you have a total of 3 zeros. It's a third degree polynomial, and so those are your 3 zeros. 2 imaginary, 1 real. Again, kind of a fun problem, kind of a neat way to see how the you can use synthetic division and your rational roots theorem and your remainder theorem and your factor theorem and all these fun things in your algebra book to find the solution to an equation that is really, in most cases, unfactorable. So, if you have any questions about this problem, please let me know.